Welcome back. So we are heading into section 6.2, talking about one application that we have for integration, and that is in computing volumes. So you'll see here I have a few diagrams drawn already because I don't want to spend 5 minutes, 10 minutes of you just sitting there watch me draw these. So you can pause it if you want to try to draw them out. These diagrams also are in the book, so you can take a look at them there. If you think that their computer-generated graphic might be a little nicer than mine. But you get a general idea. It's kind of like a loaf of bread shape here. But the idea in computing volumes using integration is we're going to be finding, first of all, what we call a cross-section. So we get a cross-section of this solid here. Okay, that's found by basically, if you just imagine, right, taking like this piece of paper and just chopping it, or get it like a knife or something and just chopping through this loaf of bread, the piece that remains leaves, right, a new shape, right, just a flat surface there. That is considered a cross section, right? So it's one slice of this loaf of bread. Now, we can use that slice to then extrapolate a volume. So here we have, right, A of x represents the area of this region. So A of x sub I star, that's just kind of fancy notation indicating that we're just taking one of the slices at kind of at random, and we're using that slice as kind of our starting point. And then we create a width around it. Okay, so you can see that's our delta x, so we have a certain width around it, and what that gives us is a new solid in here. Okay, so that gives us a solid around that cross section, and that gives us a volume. And then what we do is we just take those little cutouts, right, those little sections, and we do that all the way across. Kind of like if we were doing a regular curve, right? We would take the curve and draw our rectangular pieces in it. Same idea, but now we're actually taking volumes. We're taking solids out of these surfaces. So you can see here we have just a bunch of the different pieces taken out. You add up the volume of all of those pieces. That gives you the volume of the entire solid. And of course, that gives you an approximation. And using integration, we can then find the exact volume of a solid by just taking the integral of an area. So this is going to be the volume can be calculated using the integral from a to b of a of x dx. And that's pretty much all there is to that. So we can find volume of a solid by taking the integral of the area of one of its cross sections and evaluating that from a to b. Okay, so over the entire length of the solid. So we can actually use this. We're going to do something kind of interesting with it here. We're not going to do a kind of traditional example. We're actually going to do a little bit of a proof, not a full-on proof, but we're going to show that the volume of a sphere of radius r is v equals 4/3 pi r cubed. So if you might remember from your geometry days, right, the volume of a sphere is 4/3 pi r cubed. We're actually going to use calculus to show why that is the case. Okay? So we're going to get a sphere, and we have kind of some free will here to do with it what we like. So as you can see in my diagrams, I'm placing the center at the origin. Okay, so placing the center at the origin. That's going to make it easier to work with, especially in terms of formulas. So what we need to do is get a cross section of this. So if I get my paper, my knife, whatever, and I cut out a piece, what does that piece look like? Well, that piece is going to be a circle. Okay, I know that might be kind of hard to tell from my rather crude drawing here. But that would in fact be a circle. Okay, so just kind of imagine with a little bit of perspective here, that being cut out. So, in order for us to be able to work with this circle, we need to figure out a formula for it, basically. Okay, so obviously the radius of the sphere is r. Right, so that we know. But when it comes to the circle, so let me draw the circle right here. Okay, so that's the circle that we've kind of cut out. And our distance from the center to the center of that circle, whatever it is, that length is what we're going to call x. All right, that's the x coordinate, x component. The height, right, the radius of this circle is going to be y, right? That's its vertical component within the sphere. And this length right here, from the center of the sphere to that edge of the sphere, that's just the radius of the sphere. That's r. Okay, so again, we have the x direction, the y direction, and then the length of the radius there. Alright, so since this cross section that we found is a circle, we can come up with a formula for it. So let me go ahead and just put this down here. So our cross section is a circle. With radius y, right? Y is the radius of the circle, right? Not the sphere, the circle. And that's going to be equal to the square root of r squared minus x squared. Why is that? Because the formula for a circle, right, is x squared plus y squared equals r squared. Or you can use the Pythagorean theorem if you like, right, on this right triangle here. So there's a lot of different ways to get to that point, to make that argument. Alright. So once we have that, we can find the area of the cross section. So the area of the circle, if anybody remembers that from geometry, that's pi r squared. R in this case is y, right? That's what the radius is. So that's going to be pi r squared, so that's pi y squared. And y is the square root of r squared minus x squared. So square that, and the square and the square root undo each other. Right? Because it was the square root and then we squared it. Alright, so that's our formula for a of x. That's the area of one cross section of this sphere. Okay, so to find the volume, we need to evaluate it from negative r up to r, right? That's the entirety of the sphere. So to find volume, from negative r to r, we go ahead and set up the integral. So integral from negative r to r of that cross-sectional area. Okay, so we get negative r to r of pi times r squared minus x squared dx. And x is still the variable here. R is the radius of the sphere, which is a fixed amount. Okay, so we don't know what it is necessarily, but r is considered a constant. In this case, x is still the variable. Okay, so pi is a constant, so pi just stays out of it. Okay, r squared is considered a constant, so that's going to become r squared x when you take the antiderivative. And then antiderivative of x squared is x cubed over 3, evaluated from negative r to r. Okay, apply fundamental theorem of calculus. This is going to give us r cubed minus r cubed over 3 minus negative r cubed plus r cubed over 3. So we get pi. So if you want to distribute that negatives, that becomes a plus, that becomes a minus. So we get 2r cubed minus 2/3 r cubed. So we get, that's 1 1/3 r cubed, or in other words, that's 4/3. Right, and it's still times pi, so that's 4/3 pi r cubed, which is exactly what we wanted to get, right, for the formula for the volume of a sphere. Alright, so notice it's just kind of a cool thing that we can do with integrals, that we took an integral of a two-dimensional surface, right, of an area, and we were able to use it to find a three-dimensional volume. Okay? So let's look at a little more traditional example now. So find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals the square root of x from 0 to 1. So we have the square root function from 0 to 1. And we want to find the volume of the solid obtained by rotating it about the x-axis. So here we have, so if we were going to look at like an approximation of this, we would draw, right, like a rectangle. This, I'm just going to draw a sample rectangle. Okay, so the width of this would be delta x. Its height would be the square root of x. Okay, and then we find the area of one of these cross sections and then extrapolate that into volume. So by rotating it about the x-axis, so we're taking this curve and just going like this, just spinning it around the x-axis. So that's going to give us something like that. Okay, and then this little rectangle here is going to form a solid shape. Okay. So this is what we call a disk. Okay, so this little disk here has width delta x, right? That turns into our dx when we switch from a summation, right, an approximation to an integral. So, but this is what we're looking for. We're looking for the volume of this entire solid here. So the cross section is going to be, again, this circular disk, right, the surface there, and that's just a circle. It is just circular because it's being rotated about the axis. So we're going to have the area of that is pi r squared. All right, so we have pi r squared, which in this case, r is going to be this height, which in this case we said is the square root of x. So pi r squared, so pi times the square root of x squared, or just pi times x. Okay, so this is the area of the cross section. So the volume from x equals 0 to x equals 1 is going to be the integral from 0 to 1 of that cross-sectional area. So integral 0 to 1 of pi times x dx. So we get pi times x squared over 2 from 0 to 1. So we just get pi over 2. And that would be the volume obtained by rotating the square root function about the x-axis. All right. Let's look at another one. So find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So here we have the y equals x cubed going up to x equals 8 and x equals 0. Okay, that's how we know not to use any of the stuff down below the x-axis, because it's being bounded by x equals 0. Okay, so in this case, when we're rotating about the y-axis, so we're rotating this way, my disk is actually going to be horizontal, like this, okay, because of the way that we're rotating it. So it's going to look something like that, give or take. Okay, so what we need to use in this case is actually going to be our horizontal integration that we saw in the last section, because this height here, this width, is going to be a change in y, delta y, and when we rotate that piece, right, we get something like that. Okay, so our disk is actually horizontal this time. So our radius, which is going to be that length there, right? Because again, that's delta y on the side. That length is just going to be the x component of that function. Okay, so if we're doing horizontal integration, instead of writing it y equals x cubed, we're going to write x equals the cube root of y. Okay, so again, since we're doing horizontal integration, everything is going this direction because we're rotating about the y-axis. That means we want to use a function of y instead of a function of x. So this is the one we're going to use. So that gives us the value of our radius. So, because again, this is circular, because it's being rotated. So we have pi r squared, the radius is x. So our cross-section, its area is going to be a of y equals pi times radius squared, the radius is x squared, which is pi times the cube root of y squared, or pi times y to the 2/3 power. Okay, write that using irrational power instead. So the volume, if we were going to look at this approximating cylinder here, right, that little short stubby cylinder that we have, so the volume of the approximating cylinder, that would be area of the cross-section times delta y. But what we want is not an approximate area, right, using those rectangles, using those cylinders. We want the exact area using integration, of course. So the volume of the solid from y equals 0 to y equals 8 is going to be v equals integral 0 to 8 of pi times y to the 2/3 dy. Take the antiderivative of that, so take the antiderivative of the rational function, or the rational fraction, excuse me, from 0 to 8. And it turns out it does work out pretty cleanly because the cube root of 8 is 2 and the cube root of 0 is 0. So you don't worry about any roots in that final answer. And it turns out this one gives us 96 pi over 5 when all is said and done. Alright, so if you're wondering, oh, I didn't like that switch from function of x to a function of y, can I just do it the other way? Well, not easily. Okay, not easily at all. In fact, I would say at this level, that's probably not going to be possible because we're rotating about the y-axis here. So if you were going to do this vertically, you'd have to draw your rectangle like this, and then that would give you kind of a hollow shape like this, and then you'd have to find, some surface going this direction, and it would just be a mess to try to do that. The reason we shift our orientation and work it horizontally like that is because it gives us something circular when we rotate it around, and we know the area for the circle is pi r squared. So again, we're just trying to make it easier on ourselves, and switching over to y is going to do that for us. Alright. Let's look at another one. So bring in a new idea here. So we want to find the volume of the resulting solid when the region R is enclosed by the curves y equals x and y equals x squared, and that is rotated about the x-axis. So here we have y equals x squared. Oops. Let me zoom in here. Y equals x squared. Y equals x. Here's our region in question. Okay. And we know where these intersect, right? It's at the point 0, 0 and at the point 1, 1. If we didn't know that, we could find that without too much difficulty. So now that gets rotated, it said, about the x-axis. Okay. So we have that shape right there, roughly, and then that gets rotated about the x-axis. So let me draw that one kind of clean from scratch here. So it's going to give us something of a cone, and you can just picture that parabolic function inside there. So if we were going to take a rectangular approximation there, that would get rotated around. But because you notice there's a little bit of a gap down here, right? There's some space between the curve and the x-axis. So what that's going to do is it's going to create a hole in the middle of our surface, our area of our cross-section. Okay. So this is what we call a washer. Okay, so a washer, like the little metallic pieces you have when you're working on anything, right, doing projects with around the house, that kind of thing. They go along with all kinds of things. You can tell I'm not a particularly handy person, but we're talking about a washer that you would see just like in a toolkit. So we're looking at a volume of a solid that is not completely there, right? There's a big circular hole in the middle. Now, that's actually going to be okay for us because we notice, hopefully, that by rotating the outer portion, it gives us a circle, and the inner portion also gives us a circle. There we go. So the region in question, let me just highlight it, is this part. That's the part that we're looking at in this washer that we need. Okay, so that's in there. And we need to find the area as a function of x in this case, so that we can then get the volume. So we know the area of a circle is going to be pi r squared. The radius of the outer circle, well, what is that? We're going from here up to the top function. That function is just y equals x, which means that that radius, that value here, is going to be x. And the radius of the small one, well, that's just going from the x-axis, that center, up to the smaller function, right? The lower function. So that's going to be x squared. So that region gives us a of x. So the area is the area of the big circle minus the area of the small circle. So the area of the big circle is pi r squared, so pi times x squared, minus the area of the small circle, which is pi r squared, but the radius of the small circle is x squared. So pi x squared squared. Okay, so I know it might seem a little counterintuitive that x squared is the smaller radius, but between 0 and 1, x squared is actually smaller than x, right? And that's played out there in the graphs. So this gives us pi times x squared minus x to the fourth. So to find the volume of this solid, we can go ahead and take the integral from 0 to 1, right? That's where their intersection goes, of pi times x squared minus x to the fourth dx. So we're going to get pi times x cubed over 3 minus x to the fifth over 5 from 0 to 1, and that is 2 pi over 15. So we get the volume of that solid is 2 pi over 15, okay, found by rotating that region around the x-axis. Okay, so this method that we have, we're finding the volume of what we call a solid of revolution. So to find the volume of a solid of revolution, we integrate the cross-sectional area. That's what we've been doing this whole time. Okay, this is oftentimes called the disk and washer method. Okay, and the reason we're going to signify that is because in the next section we'll see a different way to compute some volumes. But the disk and washer method, because we are, as you saw in the previous examples, right over in this one we drew disks right here representing that cross-sectional area, and here we drew, right, a washer to represent that cross-sectional area. So this is the disk and washer method. So let's look at one more example to wrap this out. So find the volume of the solid obtained by rotating the region R from above. Oh, did I mess that up? Oh, I need to learn to read my own questions better. Find the volume of the solid by rotating the region R from above about the line x equals -1. So when it says from above, I'm talking about this one. So we're going to use the same region R. So from y equals x to y equals x squared. But instead of rotating it about the x-axis, we're going to rotate it about the line x equals -1. So let me get my graph going over here. So we have okay, so we have x squared. This is our region, and we're rotating it about this line. Okay. So, let's see, this bottom point here, when it gets rotated, it's one away from this line, so it's going to be one away on the other side too. So that's going to rotate kind of like that. It's a good practice in drawing these. This one is 2 units away, so that's going to be 2 units away in the other direction. So that's going to be like right there. And then just try to round out the graph a bit. There we go. So that's roughly what this looks like. So it's kind of like a bowl, except everything inside here is hollow. Okay, so it's a bowl, but the bottom's been cut out, basically, is what we have here. Okay. So when we are setting up the cross-sectional area, because we're rotating horizontally like that, we need to use y as our variable. Okay, so again, horizontal rotation, use y as the variable. So this is a of y. So if we have, let me just give another quick sketch here. Oops. Okay, we draw our cross-sectional area. It is a washer in this case, right, because it has that open hole in the middle around -1. So when we're looking at the area, it is going to be circular, right? So it's going to have, again, that general form of outer circle minus inner circle when we're looking for that area. So it's going to be pi times whatever the outer radius is squared minus pi times the inner radius squared. Okay, so with these functions, let me go ahead and rewrite these in terms of y. So this one, the line was y equals x, so that can just be y. This one is y equals x squared, so we can rewrite that as x equals the square root of y. Okay, so when we're looking at our distances, our lengths from the center, because again the center is right here. Well, this length from 0 to the line, that length right there, that's y, right? Because that's what the line is, it's y. And then the length from 0 to the outer function, that's the square root of y. So that would seem to indicate what our radius is, right? It would be y and the square root of y. However, we're not starting here. We're starting 1 unit to the left. So don't forget we have this extra length of 1 in here. So what that tells us is that the inner radius is going to be 1 plus that little bit extra, so 1 plus y. And the outer radius is again that same 1, but this time plus a little bit extra, so plus the square root of y. Okay, those are going to be the radii of these circles. So again, we changed to functions of y because of the horizontal rotation, and we added the 1 to the functions because we are centered 1 unit left of 0. Okay, so it has a further distance for the radius. So this is going to be pi times 1 plus the square root of y squared, right? That's the outer radius, minus pi times 1 plus y squared. That's that inner radius. So, our volume is going to be the integral from 0 to 1, right? That's where those functions intersect, right? From here to here, of that cross-sectional area. So that's going to be pi times this big function here. So 1 plus square root of y squared minus 1 plus y quantity squared. I went ahead and factored the pi out of both and just put it out here. So what we have to do in that case is we have to go ahead and distribute both of those out. So you have to FOIL them. And then combine any like terms that we have. So that's pi times the integral. And when you do that, it actually turns out not too bad. You get 2 times the square root of y minus y squared dy. Which gives us, when you take the antiderivative, that's pi times 4y to the 3 halves over 3 minus y squared over 2 minus y cubed over 3. So a lot of fractions in here. From 0 to 1, evaluate those, and you get pi over 2. Okay, so we get that region when rotated about the x-axis was 2 pi over 15. That region when rotated about the line x equals -1, so rotated horizontally that way, it gives us a volume of pi over 2. Alright, so I know that's a bit of a longer section, a lot of new stuff in this one. So that's going to be it for section 6.2. When we come back in section 6.3, we're going to look at a different method for finding volumes of solids like these. So I'll see you all in the next section.